Hello, my name is Yihe Lu. I'm a postdoc from the NAPS lab in Cardiff University. Our lab focuses on sleep research, and I study sleep with computational models. This is a pre-recorded presentation for the 2021 meeting of the Society for Mathematical Psychology. In this presentation, I'll talk about memory reactivation in neural networks. To find a minimal model for memory reactivation, I start with a minimal model for memory. A memory should serve some basic functions. It can acquire memories, that is, they can learn or store information from training data, and then the information should be retrievable in future. To ensure future retrieval being useful, it is vital for the memory to retain information. Memory retention is less considered in models because in many cases, we care only about a model's performance right after training, and the model is unchanged between learning and testing. However, this is apparently not realistic to model memory reactivation in sleep. I've been studying mainly the restricted Boltzmann machine, or RBM, an artificial neural network carrying out statistical learning. I take it as a proxy for my neocortical model because it learns slower and extracts underlying irregularities from a large number of samples. I also play around with lookup tables and MINOVA 2, which are exemplar-based models. They are more suitable proxies for hippocampus, which can learn rapidly and maintain perfectly separated patterns. To investigate memory reactivation during retention in these models, I assume that the model reuses its acquisition and retrieval mechanisms to do replay and consolidation. Note I'm using replay, reactivation, or even rehearsal as synonyms. Other than this memory consolidation effect, forgetting may also take place in sleep. For neural networks, these two effects are roughly conceptualized as a synaptic homeostasis hypothesis and the system consolidation theory, but I think it's also straightforward to extend them for exemplar-based models. In fact, a 2017 paper on Journal of Mathematical Psychology describes a mathematical equivalence between some exemplar-based models and neural networks, specifically for MINOVA 2. So I guess such extension and direct comparison between models is reasonable. Replay has been studied for a long time in artificial neural networks. It is also a commonly used strategy in machine learning. We use replay to overcome the catastrophic forgetting problem, which is rooted in the stability plasticity dilemma in nervous systems. People started with experience or exact replay ER, which mixes old veridical training data with new data when the model is trained for a new pattern or a new task. Many and more recent works investigated GR, short for generative replay, which deploys a generative model to reconstruct pseudo training patterns while learning new data. Moreover, I tried to model TMR, targeted memory reactivation, a new technique for interfering brain activities during sleep. This is the kind of thing my experimentalist colleagues do in our lab. In wakeful learning, an additional sensory cue, typically auditory or olfactory, is paired with a learning task. During sleep, this sensory cue is represented, presumably triggering the cued memory. Real-life experiments have shown this technique effective in enhancing the performance of the cued task. I'm mostly interested in how these replay strategies modulate the performance of a neural network. People have studied ER and GR a lot, but few computational models have considered TMR. To model TMR, I simply present partially masked training samples as cues instead of randomly generated samples. And I call this strategy cued generative replay. Before showing my simulations, let me talk briefly on how I measure test performance and replay quality. I use these two general measures: classification, accuracy, and reconstruction similarity for recognition and recall tasks, respectively. I model any pattern as a vector and partition it into two areas, where the first area encodes task-related information and the second area encodes the paired cues or context information. When measuring accuracy or similarity, I consider this task information area only. To measure replay quality, I use exactness and evenness. Exactness can be any similarity metric, but in my simulations, it is just a weighted cosine similarity between any replay samples and true prototypes. Evenness is taken from the biodiversity literature. The replay frequency can be considered as a probability distribution, and the evenness is obtained by dividing the entropy of this distribution P by log n, the number of categories. One is the largest value for both these measures. Exactness equal to 1 means perfect replay samples. Evenness equal to 1 means uniform distribution. I'll talk about my simulations in continual learning and batch learning scenarios. I did continual learning first because traditionally replay is used in this context, so it serves as a sanity check for my replay quality measures. But later I started to run cute generative replay, so I went back to batch learning. I only investigated RVMs in this continual learning simulations because catastrophic forgetting is not a problem for exemplar-based models like a lookup table. I set 10 categories for my RVMs to learn sequentially. I plot the test accuracy at every learning stage. I also draw the curves for exactness and evenness right before the model's learning outcome. The red curves are for ER and the orange curves for GR. We can see when the number of replay samples are very big, ER outperforms GR here. However, given a smaller replay number, GR is actually better. It is also very interesting to see when there is only one replay samples at every stage, the accuracy stays at 20% instead of the chance level 10%. These are all evidences confirming a recent speculation about GR that as long as a category gets some replay, even for just once, the corresponding memory trace can be maintained. This speculation also inspires me to use the evenness index because the more uniform the replay distribution is, the more likely each category gets some memory reactivation. Now in these simulations for batch learning, I started to investigate TMR, targeted memory reactivation. Here I train my models with just 5 categories, and they are trained through 10 wake sleep cycles. There are 10 epochs in every cycle, 5 for wake and 5 for sleep. I will show the training curves for my RVMs in the next slide, but to begin with here, I show you these results of the lookup table and MINOVA 2 in the first column, and zooming plots for the very first 2 cycles in the second and third columns. They are boringly periodic or periodic boring, as their learning curves and the replay quality are completely driven by the wake sleep cycles. Of course, lookup table and MINOVA 2 are both great fast learners. They become excellent after a handful of epochs and remain pretty good, even though you see these performance drops during sleep. What happens is by pure randomness, GR samples are skewed towards the most favorable memory trace in sleep, which is unfortunately not good for test performance, but the performance is picked up rapidly in subsequent wakes phases. Now I'm showing you the complete figure down here. Notably, the blue and purple curves are exactly the same as in this first plot. I put them here as a background for comparison, and our focus is on the RVM oranges. We can see the RVMs have distinct learning curves for different replay strategies. The NR no replay curve grows slowly by about 0.2% per epoch. The ER curve does better, about twice as good as NR. The GR and TMR curves have this periodic feature similar to lookup table and MINOVA 2. However, they show a characteristic performance rebound in subsequent wake phases. Even so, the overall performance of GR is still similar to ER, but I think it's safe to say the TMR is almost always the best. Moreover, after 100 epochs, I ethically deprive my models from sleeping because I want to see the orange curves converge together without wasting too much time and electricity, but I was not patient enough to see that, so I'm just claiming here recklessly that memory reactivation could in practice have a final state effect in neural networks. I can also see TMR helps the RBM build up replay evenness gradually while keeping a high score in exactness. And this is my explanation why TMR or CGI is the best replay strategy in my simulations. However, this learning dynamics has little to do with the real-life TMR experiments in our lab because human subjects usually spend only 1 day in training and 1 night in sleep in the lab, rather than being constantly exposed to training data. Nonetheless, my PI Penny Lewis suggested that the learning dynamics look similar to the developmental learning of bird song. This learning curve down here. This is the learning dynamics of a male zebra finch, a songbird, throughout his development when he learns a song consisting of several syllables by imitating a tutor. There are many details I'm omitting here, but the main results as shown in these figures are the positive correlation between post-sleep performance deterioration and wakeful learning improvement. And the amount of this deterioration is getting smaller and smaller throughout development. For a 1-year-old bird, his song is almost stable in terms of the individual syllables and the whole song structure. To adapt my idealized model to this real-life example, here I make some assumptions to simplify things. I consider a song as a matrix containing a batch of syllables. Each syllable is divided into 2 pieces. The first piece encodes acoustic features, and the second piece encodes its temporal features. So song ABC is different from CBA when they differ in the temporal part of this matrix. For simplicity, I assume there's an additional mechanism perhaps taking place in the bird's hippocampus responsible for generating temporal sequences. So the temporal cues here are internal cues rather than TMR cues that are externally presented by experimentals. I'm only concerned about the goodness of my model imitating the sound of the syllable, so I test my model by presenting the temporal cues and checking how similar the true patterns, the acoustic features are. This is also how I conduct cued generative replay, CGR, in my model. Of course, lacking sequence generation is a limitation of my model, but checking individual syllable changes is exactly what is done in the first half of the original Birdsong paper. And for comparison, I do vanilla GR2, which effectively randomizes the temporal part as well as the acoustic part. In addition, I also modify NR, no replay, by adding some forgetting. This is useful because it will be interesting to check whether the synaptic homeostasis hypothesis or the system consolidation theory explains this learning curve better. This is the performance of my RBM with the 4 memory reactivation strategies. I'm not showing the results for lookup table and MINOVA 2 because they look very similar to the plot in the previous slides. In each wake sleep cycle, the RBMs would do 10 epochs of wakeful learning followed by 30 epochs of sleep. The blue curves is for NR, the yellow, the orange for ER, the green for GR, and the red curve for cued generative replay, CGR. We can see CGR does give the more similar learning dynamics to the Birdsong data. It is very different from the normal GR, the green curve, which implies the significance of reconstructing accurate internal temporal cues in replay. I'm also showing you the replay evenness and exactness below the performance plot. I'm not going to describe the details. The main point is, like in previous TMR simulations, a higher evenness makes CGR outperform ER and GR. Here are some further follow-up data analysis plot. The middle row basically checks whether post-sleep deterioration is positively correlated with subsequent wakeful learning. So actually, forgetting survives this analysis in addition to cued generative replay. However, if we look at the bottom row, it's clear with only cued generative replay, the post-sleep deterioration decays throughout development, while the deterioration with forgetting kind of increases. To summarize, I propose a minimal memory replay model by reusing memory retrieval and acquisition as memory replay and consolidation in minimal memory models. My simulations confirmed that memory reactivation can help RBMs accomplish continual learning, and I found the effect of GR generative replay is dependent on the amount of memory reactivation. It can be better than ER, experience, or exact replay if the amount is relatively small. In addition, I show the usefulness of cued generative replay in RBMs in batch learning, and there is a characteristic performance rebound after every sleep phase. I'm using it to model TMR experiments where external sensory cues are used, and also to model developmental learning of bird songs, which relies on internal temporal cues. That's all. Thank you.